military, so probably we won't see so much in the next 3 years, or a little bit less. So what's the title of your talk, Gal? And maybe you can share the screen now.
So first of all, a quick correction. I have not yet received my PhD. I'm still waiting.
Oh, not yet. Okay.
I have submitted my thesis, but the referees have not yet given all of the responses. So I'm not.
Okay.
So some work remains, but okay. So.
Okay, so we say PhD minus epsilon. Okay, good. So you can all read, and I give the word now to Gal, and please.
So hello everyone, my name is Gal. I'm going to give you a lecture today about GL2 modules and how we can give them some exotic symmetric monoidal structures and what this means for automorphic representations. So a couple of words. First of all, some of you have already seen my lecture in the Weizmann Institute. If so, then it's going to be the same lecture. I apologize, but so you might be bored. So this is an apology in advance. Second of all, please, if something is unclear, interrupt me. Let me know so that I can clarify or explain. Probably okay. So I'm going to maybe be doing something that using terms, or if I use a term that you're unfamiliar with or something like that, then just let me know. There's going to be some category theory here, which maybe some people are more or less comfortable with it. So just again ask questions and I will reply. Okay, so let's maybe begin. Okay, so L functions are important objects. They're so important that they deserve a slide of their own, but more specifically, they're a big deal. Yes, you have different kinds of L functions that can come out of various different kinds of constructions. Sometimes they come out of representation theoretical objects like automorphic representations, and sometimes out of Galois representations. And when they're similar, then you get some deep connections. However, this is not what I'm going to be talking about today. We're going to be focusing only on automorphic L functions. Now, basically, L functions, automorphic L functions are usually built with this kind of recipe or a complicated construction that is not just as straightforward as saying, here is an L function, that's a formula, substitute stuff into it. Basically, what you do is that there is someone magically conjured up a formula, which is called a zeta integral. This formula accepts some data. Maybe it's a vector in your representation, maybe it's a matrix coefficient, maybe it's some test function on some other space. And this extra data gets fed into some mechanism that produces a zeta integral. And then out of this entire collection of zeta integrals, there's some recipe to choose a distinguished representative. And this distinguished representative is called the L function. Now, this is a pretty complicated process, and it's highly non-trivial. Just as the simplest example is that even in the case of GL2, just the easiest, maybe one of the easiest cases automorphically, there are actually two completely different zeta integral formulas that give the same L function, but it's really, but a priori, when you just look at them, there's no reason that they should be the same. There's no like a really nice explanation that says, oh, these two things are equivalent. They very much don't look the same. So for example, there's the Godmet-Jacquet zeta integral. It's just one way to attach zeta integrals to automorphic representations of GL2. This uses pairs of vectors or matrix coefficients. And there is the Jacquet-Langland zeta integral, which uses just single vectors from the representation. And so these things are very, very different. They depend on completely different data, but they give the same L function. So that's a very strange phenomenon, and it illustrates that zeta integrals have something interesting to them, and a lot of people have worked on this. If I start listing names, then people will be insulted because I missed some, but this is something that's a lot of people are interested in, and they try to give some meaning to understand these zeta integrals. Why do they appear? Why is this zoo of formulas? Now, in this talk, what I'm going to be focusing on is specifically the equivalent, is specifically this specific pair of zeta integrals, the Godmet-Jacquet zeta integrals and Jacquet-Langland zeta integrals. And what I'm going to do is that I'm going to give proof that the associated L function is the same, not by some algebraic manipulation of the zeta integral of the L function, but instead by basically categorifying the question. Basically, what I'm going to do is that I'm going to say, instead of considering just the single representative, which is the L function, which is a GCD of some class of objects, instead I'm going to do this to show that the entire class, the two classes are actually the same. They're isomorphic in some strong sense. In other words, you can think of it as instead of people usually, when they talk about vector spaces, then when they start out, they work with explicit bases. Yes, they think of a vector space as the space spanned by this specific base. But it's very beneficial for us as mathematicians to instead work with not with explicit bases, but with the entire vector space, and just forget that it may or may not have a basis. And this is similar to what we're going to be doing here. Instead of looking at the generator for the class of zeta integrals, which is the L function, I'm going to be comparing the entire class, which is in this analogy the vector space. And what's going to happen is that once I do that, I'll get some really interesting things that just pop out of nowhere, that unprompted. I didn't, without putting them in, they suddenly pop out. So just one example that we're going to be spending a lot of time on is that, well, if you have a class of zeta integrals that's parameterized by pairs of vectors and another class that's parameterized by single vectors, and you have a correspondence between them, then that means that you have some kind of bilinear correspondence. Yes, you have a multiplicative action. And this will turn out to induce some exotic multiplicative structure on both p-adic and automorphic representations. And that's going to be the main focus of this talk. Now, as was mentioned earlier, everything I'm going to say is part of my PhD thesis under the supervision of Joseph Bernstein. Okay, so how is this talk going to be structured? There's introduction, which I just did. There's I'm going to say a few words in fixed notation about p-adic representations. Then we're going to start comparing this Godmeasure K zeta integrals versus Jacquet Langland zeta integrals. We will derive the associated monoidal structure. At that point, I will apologize. And finally, we will describe what this means in the global theory rather than the local p-adic theory. And maybe I'll say some words about automorphic representations and what it means for a representation which is not necessarily reducible to be automorphic. Okay, so any questions before I begin? Okay, so good. I may be talking a bit too fast, so if I'm doing that, please let me know. Okay, so let's fix notation. So F will be a local field. It is going to have characteristic nodes 2, and we denote G by GL2F. I say that G module is smooth, and I consider the category of smooth G modules, which I call mod G. If every vector is fixed by some neighborhood affinity, and I denote the contragradient duality, where each vector is sent to the smooth covectors by V tilde. One more piece of notation that I'm going to say is that a G module for GL2F is called generic if it has a Kirillov or a Whittaker model. Basically, that's it's for an irreducible representation. What this means is that the representation can be embedded in some space of functions that is equivariant with respect to some unipotent subgroup. The details will probably pop out naturally during the rest of this lecture, so I won't go into the definition itself right now, but that's just, it should mean something to you. So that we have some fixed language. So you know what I mean when I say generic representation. Okay, so let's begin discussing the L functions themselves. So I said that I was going to compare two constructions. The first is the construction by Godmeasure K. Basically what happens is that you are given a matrix coefficient, just a function on the group that's defined by taking a vector, multiplying it by a function and multiplying by a covector. And you take a test function. For us, a test function psi is going to be a smooth, compactly supported function on M2F. Now, given this data, you can compute what's called the Godmeasure K zeta integral. Basically, you integrate the matrix coefficient against the test function with some weight. that's related to the multiplicative group. This is a meromorphic function. This depends on psi, beta, and S, where S is a complex parameter. It's a meromorphic function in S. In fact, it's a rational function. And when you take the GCD of all of these rational functions, then the result is called the local L function of your representation. Now, that's one recipe. That's the first thing I'm going to compare. The second thing I'm going to compare is called the Jacquet-Langlands zeta integral, or this is actually it was pointed out to me that this integral was essentially by Hecke. So in this case, what you start is that you start with what's called a Kirillov model. For the moment, let's think of it as a function that takes a vector in my representation and returns a function on F on the field, a complex function. It has to be to satisfy some equivariance properties, and if it exists, then it's unique up to scalar. So I'm saying that one of the ingredients for this recipe is a Kirillov model, but really you don't really have much of a choice. It is essentially unique. And the second ingredient is just the test vector, so just any vector inside your representation. And you integrate them against one another. Basically, you take the test vector, you turn it into a function on F, and you just integrate that as that function across F star. Once again, it depends on a complex parameter S. This is a meromorphic zeta integral. It's a rational function. You can use the GCD and you get some L function out of it. Any question before I proceed? Okay. So now it's possible to show by direct computation that these two things are always the same. That you can just go over all possible irreducible representations. You can compute their zeta integral, their L functions, and show that they're the same. But we want to compare the spaces of zeta integrals other than just the L functions. And we're hoping that we'll have a more conceptual proof since we're not looking at a specific representative, whose choice might not really be canonical. So how do we do this? First of all, we need to understand what our spaces of zeta integrals are characterized by. That is, I need to understand what is the input data for a zeta integral. So essentially, I just said what it was, right? You take a matrix coefficient and the test function. But that's Yes, sure.
Ask a question. So sure. Can you explain this a little bit more? This Godman-Jacquet and Jacquet-Langlands. I mean, there were two zeta functions which had different ingredients, right?
Yes.
So what do you actually mean by this equality? Can you explain this once more? I wasn't getting it.
So when you take both of these functions give you some collection, some set of zeta integrals, some set of functions that depend on a complex parameter. Now, from these sets, you can choose some canonical representative, which is called the L function. It's a GCD for all of these rational functions, and the GCD and these two GCDs are just known to be the same. They have the same GCD, and it's also possible to use this to show directly that the two sets are the same. So any zeta integral that's achievable here is achievable here. But that's a terrible proof. Yes, it's unclear. It's not really understood what's going on. And the proof that the two L functions are the same is just basically by computing them for all cases. That's awful. Instead, what I'm going to do is that I'm going to give you something more. So you're asking what I mean by equality. Here is what I mean by equality. I'm going to give some correspondence between the data that parameterizes each of the constructions. So I'm going to have correspondence between the data that gives a Godman-Jacquet zeta integral and the data that gives a Jacquet-Langlands zeta integral. And then I'm going to show that this correspondence I'm going to give a canonical correspondence, and then I'm going to say that this correspondence gives the same zeta integral. So if you have a piece of data here and a piece of data here, then they give the same zeta integral. In fact, the construction goes the other way around. I'm saying I want to identify something coming out of here with something coming out of here if they have the same zeta integral. And this will turn out to essentially define a correspondence on the data, which I will then construct explicitly. Okay. Okay, so let me try and explain what I mean by the data that gives a Jacquet-Langlands zeta integral, data that gives a Godman-Jacquet zeta integral. So as I said, for a Godman-Jacquet zeta integral, it's given by some matrix coefficient in the test function, but there's some redundancy in this data. So first of all, matrix coefficient is, for the moment, let's think of it as a vector in the space and the dual vector and the vector in the control gradient space. But if you take a look at this formula, then, well, if you do a translation on beta, if you translate beta by some element of the group and you translate psi by the same element, then it doesn't give you quite the same z integral, but up to, if it has determinant 1, then it does. So you can do this for left translations. You can left translate g and left translate psi. You can do this for right translations. You can right translate g and beta and right translate psi, and that gives you the same the same zeta integral. So there's some redundancy here in the data. Some pieces of data that canonically give the same function, the same zeta integral. So essentially, I can think of it as like I have v and I have v tilde, and I take tensor products on the left and right over G with the functions on M to F. Unfortunately, I only want this to be true for matrices that have determinant 1. So basically, one way to correct this is to think of it as if I have functions on M to F times F star, and then I take tensor product over G from the left and right, where I say that G acts on the left on this space on M to F times F star by multiplying the matrix and acting by determinant on F star. And it also acts on the right by multiplying the matrix from the right and multiplying F star by the determinant. And so this guarantees that this is essentially the same as writing just the tensor product over G with M to F, but where I only allow moving elements of G across the tensor product if they have total determinant 1. So that's the same as putting an F star here. So this is one. So for every element in this vector space, which is the tensor product of V S of M to F times F star and V tilde, I get a good measure K zeta integral, and this doesn't have any obvious redundancies anymore. So that's the space that I'm going to say that parameterizes good measure K zeta integrals. That's, for me, elements of this space are going to be the elements of the space of zeta integrals. And then there is the space of Jacquet-Langlands zeta integrals. So that now they are characterized much more simply. As I said, there are only 2 ingredients. One is a vector in the representation, and the other is essentially unique, is a Kirillov model. So just for the moment, let's think of this space as just being V. So any element of V gives a zeta integral. So basically, here is I have all of the setup I wanted. I have 2 spaces that parameterize zeta integrals. One is V tilde times this space of functions times V, and the other is just V. And I promised you a correspondence between them. So my claim is essentially that for a generic irreducible representation V, there's a canonical isomorphism between these 2 spaces, up to choice of Kirillov model. And moreover, I claim that this canonical isomorphism respects zeta integrals. So if I take the zeta integral of the left-hand side and the zeta integral of the right-hand side, I get the same zeta integral. In fact, this property of respecting zeta integrals essentially determines this isomorphism uniquely. But okay, so now basically, I've given you some philosophical arguments for why we would hope that something like this exists. It would be very nice if I could have this kind of correspondence. But let's say that you see this for the first time and you want to prove this isomorphism, or you want to look at its properties and maybe understand what it should be. Then, well, the first thing that you do is that you observe that there's something very strange about this isomorphism. Actually, 2 different very strange things about this. The first is that it's nonlinear. The right-hand side depends on V linearly. It's a linear functor. And the left-hand side is not. It has something that's more quadratic, maybe. So that's one thing that's strange with this correspondence that I'm promising you. And the other thing that's strange is that, well, V is a G module. It's very clearly a G module. I started with a G module. But the left-hand side here, V tilde times this space times V, there's no a priori reason to suspect that it is a G module, right? It's functions on M to F times F star already carry a G times G action. They carry a left and a right G action, but I already used those 2 actions up to tensor them with V and V tilde. So how can it be isomorphic to a G representation? if it is isomorphic to a G module, then that means that there must be a third action of G on this space. So basically, essentially, the only way that this would make sense is if this underlying space of functions, M to F times functions on M to F times F star, had a third hidden G action that commuted with both the left and the right G actions. So now once you know, so first of all, claim there is such a third action. It's very easy. It's not that all that difficult. I'll show exactly what it is in a moment. So this space Y, which is functions on M to F times F star, has a G times G times G action. And once you know this, then you immediately know that V tilde times Y times V is a G module. It has another G action. And once you know it's a G module, it's not very difficult to show that this G module is specifically V, that this is the G module that it is equal to. I won't show this, but it's not really difficult. So instead, I'm going to show you why this third action exists. Or at least I'm going to very briefly discuss it. So what happens? How do we construct this hidden action? How do we, once we suspect that something like this should be around, how do we build it? So I'm going to say an explicit construction. If you lose me at some point, that's fine. I'm not going to go back to it. You don't really have to remember it. And the slides should be available, so you can just read it anyway later. But anyway, I'll tell you what Joseph told me when I showed him, when I told him that there should be a third action hidden there. He said that the only way that there can be so many commuting operators is if the Weyl representation is hiding somewhere around here. And it turns out that he was completely correct. So let me give maybe a short construction. So take a two-dimensional symplectic space with explicit basis in 1 and D2. So we have a symplectic space over a two-dimensional space over F. And well, now consider the group of GL2F cubed with determinant 1. So just triples of elements in G whose product of determinants is 1. As it turns out, this group can be embedded inside the symplectomorphisms of U times U times U. In other words, U tensor U is an 8-dimensional space, and the part of G cubed that has total determinant 1 acts on it. How does it do so? You can just, if you have U times U times U, then you can act with one copy of G on the first coordinate, with another copy of G on the second coordinate, and with the third copy of G on the third coordinate. And these actions obviously commute. And what they do to the symplectic form is that they multiply it by the product of determinants. So if you have 3 matrices whose total determinant is 1, then they act on this U times U times U in a way that respects the symplectic structure. So we have an embedding of GL2 F cubed with that one, with determinant 1 inside the symplectomorphisms of this space. And if you have a symplectic vector space, then you can, and you have some Lagrangian subspace inside it. In this case, U times some specific vector, which we call, which we identify with M to F. Then the space of functions on M to F carries a Weyl representation. So there's an action of the metaplectic group, which is a cover of the symplectic group of U times U on this space of functions on M to F. And now what happens is that I have an action. In particular, it turns out that the action, the embedding of GL2F cubed inside the symplectic space, the group, lifts the metaplectic group, and that means that GL2F cubed with the determinant 1 acts on functions on M2F. Now we just use compact induction from GL2F with determinant 1 to GL2F cubed, and this gives you that you have an action of G cubed on functions on M2F times F star, which is the Y that I promised, that should have a triple module structure. Any questions about this construction? Okay, so let's maybe take a step back. So I dived into a lot of technical details, but
I have a question. So how is it sitting? So it's sitting inside SP8, everything?
Yes.
8 by 8 matrices. So how are these 3 GL2 blocks sitting?
They're not blocks. It's a tensor product. So they're all multiplied by each other. Yes, you have if you have three matrices, then you embed them by taking at every point you have a product of one from here, and one from here. Yes, it's a degree 3.
No, this I understand, but at the end of the day, you have 8 by 8 matrices and you have some blocks sitting in there, no? 3
No.
commuting GL2s inside SP8.
Yes. So, yeah. So just it's yeah. They're just duplicated. Yes, it's so yeah. You have like you can think of it as if you have 4 blocks of one copy of GL2 just copied across the diagonal, and then you can think of like every pair you have like another dimension. So you can the second copy of G acts like in blocks that are arranged differently. And the third
If I look at the Siegel parabolic, then I take the diagonal and I take the 2 other entries, and then each one of them I extend to a copy of GL2. Is that right?
I'm not sure what is the construction that you.
Okay, never mind. I'm just trying to visualize it. But
Okay,
that's fine. I'll do it later.
So okay. So in any case.
Excuse me. Can I ask something? Is it Is it actually an embedding? Because if you look at the maximal torus of these 3 copies of GL2, it has dimension 5. Is it true? You have like 2-dimensional torus of each copy of GL2, right?
Yes. You're right. You're correct. I mistaken. The center of each copy is the same. Basically, that's. Is that what you mean?
Yes. So I wanted to ask. You said that the embedding or whatever this map, the image of this map splits in the metaplectic group.
Yes.
But the whole torus doesn't split over metaplectic group of SP. So you must have a subgroup of a torus, right?
This isn't the full torus for SP8. It's not the.
It is not, right?
Okay. It's something much smaller. Just it's the reason that this splits is just that as I was saying earlier, you can think of each copy of G as just being like in several blocks repeated multiple times. So each copy of G acts in a way which is it acts like doubly. Yes, if you just track what happens to the like if this was a real calculation, then you could track what happens to the fundamental group of GL2. Then because you have like actions of GL2 here in several blocks, then it double covers the fundamental group of SP8.
And then just curious, what would be the centralizer of the image in the metaplectic group?
So
would it be trivial?
So I suspect I haven't tried to compute it. I think it should be trivial, but I think it should be trivial.
Okay.
I'm sorry. One more question.
Yes.
So is it SO44 is SL2 times SL2 and SP2 is SL2. So is this the dual pair SP2 and SO4?
Yes, it is.
Oh, okay. So that's why you have 3 of them. So it's just SP, it's the dual pair SP and O.
Yes. It's a dual pair. Usually people don't think about it because it's repetitive somehow. Yes.
No, but it's just very small, right? So that's just why are the 3? Okay, there's usually 2, but the SO4 is SO3 times SO3.
Yes. This is exactly what's going on.
Now I understand. Thank you.
Maybe I want to say something here. It's just something very elementary. Because Nadia asked about the centralizer. If you take 3 irreducible representations, like GL2 on the space U, then the tensor product is irreducible. So by Schur's lemma, the whole commutant on the 3-fold tensor product is the scalars. And so it has some sort of central, the centralizer is is central. And the other thing is, if you take two symplectic forms and you take the tensor product, you get a symmetric form. But if you take three, then you get again a symplectic form. Yeah? And each of this GL2 or SL2 is SP1, preserves the symplectic form. So automatically, so three copies, I mean, some sort of will preserve this product form. So I just wanted to say this, I mean, just for the younger people. For the older one, it's probably all clear. Yeah, thank you.
Okay, so we dived into a lot of technical details and maybe some people lost the discussion, but that's fine because we are now going to take a step out. Let's take a step back. So let's go over what we had. We had this good measure K zeta integrals and we had J.K. Langland zeta integrals and we wanted to compare them. So we wrote down what kind of space parameterizes the good measure K zeta integrals and what kind of space parameterizes the J.K. Langland zeta integrals. And then we compared them and we deduced that we should have this triple module structure on this space Y of functions on M to F times F star. And once we did that, it was pretty straightforward to show that there was actually a canonical correspondence between these two sets. However, the thing is that tri-modules are very, very strange. As was already mentioned here, 3 is surprising. Yes, you're used to only having 2 things that act on a space. You're not used to having 3. You don't just, everyone has encountered the bimodule naturally. Yes, bimodules occur everywhere. Everything is a bimodule. But tri-modules are very much rarer. Yes, it's not every day that you do some mathematical construction and out pops a tri-module. So if you have something that's so strange, then it somehow begs for an explanation or to be placed into some mental framework. So just the moment that you see this, you should ask, what is this tri-module really? What's going on here? Because tri-modules don't just occur. So the trick is that instead of thinking about this Y as a triple module, which you can, but it is strange, you should think of it as a bifunctor. Basically define, if you have 2 G modules, V and V prime, then we define the product, or this exotic product of Y and of V and V prime, we define this Y product to be V tensor G with Y, tensor G with V prime, where we used one action of G to tensor with V, another action of G to tensor with V prime, and the third action of G gives you an action of G on the result. So you have, so you take 2 G modules and you get a new G module out of them. And this is a bilinear functor. This is a bifunctor. So unlike triple modules, which are rare, they don't come up naturally. Bifunctors are much more common. You see them all the time. And usually when you see them, they come in the form of a tensor product. Yes, you have some symmetric monoidal structure on some category, and then the symmetric monoidal structure is naturally a bifunctor. Oh, okay, so at least it's in some more decent framework now, but this begs a really natural question that, is this bifunctor a symmetric monoidal structure? And it would be really surprising if it was, because we didn't construct this functor by trying to use some operation or define anything that would make sense, that would naturally give you a multiplicative structure. We just said, okay, there's some correspondence between zeta integrals, and naturally it makes this, it constructs this bifunctor. And it is, now, although it's surprising, this actually turns out to be true. Basically, it turns out that there is an essentially unique extension of this bifunctor of this Y product to a symmetric monoidal structure on mod G. And now this is somehow extremely surprising. It's just, when you try to put this into a mental framework, this result just pops out of nowhere. And just to explain what this means is that this means that there is some object, some G module, which is a unit, so that when you use the Y product of this unit with anything else, then it stays whatever the anything else was. There's a canonical, so that's one thing. It means that this is symmetric, that the functor is symmetric. It means that it is associative. Now, associativity and even unitality, even having a unit, is not just, when you have an algebra, then being associative or having a unit is a property. But for a functor, this is an extra piece of structure. You need unitality data, and you need associativity data, which may not be unique. And what I'm claiming is that not only do all of these pieces of data exist and are compatible with each other, but also that there is an essentially unique collection of this data that corresponds to this monoidal, to this bifunctor. So essentially, you need to have some natural isomorphisms, yes, between the various different kinds of composing this bifunctor with itself. So now just to avoid being mysterious, because I just said that there is a canonical object, yes, which is the unit for the symmetric monoidal structure. So I can just tell you what it is, so that people, so just to be concrete, this is called the Whittaker. It turns out to be something called the Whittaker space, which was actually discussed here just a couple of days ago. Basically, for me, it is going to be the space of smooth, compactly supported functions on GL2F mod U2F, which are equivariant with respect to the upper diagonal matrices. So just functions on GL2F that are equivariant with respect to some additive character and smooth, compactly supported, etc. And it turns out that this Whittaker space is the unit for the symmetric monoidal structure. Now, once we formulated things this way, we think of it as the Whittaker space being a canonical object that's related to this monoidal structure, and we think of Y not as an object but as a symmetric monoidal structure, then we can reformulate the earlier statement that I had about this equivalence of the two spaces of zeta integrals in much nicer language. What do I mean? So first of all, I need to state some observations. The first one is that if V is an irreducible G module, then the space of maps between this unit object and V is either 0 or one-dimensional. And it is one-dimensional exactly if V is generic, what we said about having a Kirillov model. In fact, the data for map between the Whittaker space and V is exactly the data as a Kirillov model. Having a Kirillov model is just a map between 1 and V. And now I can reformulate the earlier statement. So what was the earlier statement? That the comparison of the two kinds of zeta integrals. Well, on one side, I had essentially V times V with this bifunctor. And on the other side, I had V, but up to a choice of Kirillov model. So I can tensor it with the one-dimensional space home between 1 and V. So if V is an irreducible generic representation, then home between 1 and V is one-dimensional. I can consider V times home between 1 and V. Now, in every symmetric monoidal category, there's always an isomorphism between V and V times 1. So there's a canonical isomorphism between V times this home space and V times 1 times this home space. And if you have an element in 1 times the home space, then that canonically maps to V. So in other words, there's a canonical morphism just coming out of the axioms of a symmetric monoidal structure between the left-hand side and the right-hand side. And as it turns out, this specific map is precisely the map that we constructed earlier. And the only content that is left to the claim earlier is that this map is not just a map, but it is an isomorphism. Not only that, but in fact, the fact that it is isomorphism also follows completely formally. It turns out that in any abelian symmetric monoidal category where the tensor product is right exact, then if you have a surjection between the unit object and V for any object V, then automatically this map V tensor home from 1 to V times V is an isomorphism. In our case, this is true because if there is a map between the Whittaker space and an irreducible representation, then this map is always surjective because the representation is irreducible. So in fact, the entire earlier statement about having this map that comes out of respecting zeta integrals immediately follows just formally from properties of symmetric monoidal categories and just having and the fact that the Whittaker space is the unit for the symmetric monoidal structure. So in other words, just forget about what I said earlier about zeta integrals completely, and or rather we can say that this symmetric monoidal structure somehow gives a natural isomorphism which respects zeta integrals. I'm not sure how clear I was. Any questions?
To be honest, I missed the step of this last arrow. I mean, I understand. I mean, that this new tensor product, you can put the one y here. So how do you get the second y here? So can you explain this once more? I mean, I don't really know what a symmetric monoidal structure is, what you actually use here, that this ordinary tensor product sign is then converted in this new symmetric monoidal structure sign. Sorry for this naive question.
No. It's perfectly fine. So what happened here is that I essentially I went through 3 steps. So step 1, I had V times this home space between 1 and V. The second is that I just used that V is isomorphic to V tensor 1. Yes, if I have a unit for some monoidal structure, then I can just, everything is canonically isomorphic to itself times 1. There's a natural isomorphism. So this is the isomorphism between the first step and the second step. Now, here what I do is that I just say, look, I have 1 tensor home from 1 to V. This is just the G module. But this G module has a canonical morphism to V. Yes, because if I have an element in 1 and a map from 1 to V, then I get an element in V. So there's a canonical isomorphism between 1 times home from 1 to V. So I just I used some associativity here without explicitly saying it, that I replaced the order of this Y product with the usual tensor product. But essentially this is the only thing that but essentially what happened is that I sent V to V times 1, and then I paired off this 1 with the map to get an element in V. So this defines a map between V times home from 1 to V times V. And it is easy to use just general abstract nonsense and the fact that the map from 1 to V is surjective to show that this map is an isomorphism. And now the non-trivial claim I'm saying is that this is the same map that I described earlier, that this map respects zeta integrals. That the right-hand side can be thought of as parameterizing Godmet-Jacquet zeta integrals, and the left-hand side can be thought of as parameterizing Jacquet-Langlands zeta integrals. And if you take the Jacquet-Langlands zeta integral of the left-hand side and the Godmet-Jacquet zeta integral of the right-hand side, then they coincide.
So your category actually has 2 tensor products, and they play nicely with each other.
So it's more specific. Maybe the easiest way to say this is that you can think of it is that it is it's okay. So there are various formal ways to say this, but essentially you can think of it as the same way as if you have an algebra over a vector space, then or an algebra over a field. Then there's you have the algebra and you have its multiplication, but it's also a vector space over the field. And the multiplication by elements of the field plays nicely with the multiplication of the algebra. Here I just had this tensor product with just a vector space. It takes the vector spaces are the same as the field, the base.
Okay, you're tensoring with a vector space. Okay,
yes,
okay.
Yes.
All right, I missed that. I thought you were tensoring with a module.
yes, I have tensor module times vector space. That's much simpler.
Oh, okay, that's fine.
Yes.
So if I may ask another question.
Sure.
So how does the structure depend on the Whittaker character?
That's an excellent question. So obviously it does because the Whittaker space depends on the Whittaker character. In the case of now, of course, in the case of GL2, all of the Whittaker characters are equivalent. Yes, they're all
right.
They're all conjugates, but it doesn't mean that you can ignore this. Yes, it's just there's still a choice here. It's just that the fact that all choices are equivalent doesn't mean that there's no dependence. Just that the dependence is somehow can be fixed by conjugation. But yes.
Okay, thank you.
So I have a question. So is there any way to define the inverse of the map? So you have the isomorphism. So is there any way to define the inverse?
So that's a good question. The answer is yes. Basically, what you do is that you can cheat. The way that I stated, you can do it as follows. the left-hand side is a vector. You can think of it as a vector in the Whittaker model for V. So basically what happens is that if you have a vector on the right-hand side, which is a pair of vectors and the test function, then you can compute its zeta integral as a complex function of S. And if you take the inverse Mellin transform of that, then you get, if you basically pretend that this function was the Mellin transform of a function on F star, which is what happened here to get the zeta integral from the left-hand side, then you should get the same thing. So if you take the zeta integral of the right-hand side and you take the inverse Mellin transform, then you get a function on F star on the left-hand side, and this function is a function in the Whittaker model of V, and that's the map. You take the Jekyll-Langlands zeta integral, you take its inverse Mellin transform, and that gives you a vector in the Whittaker model of V.
Kirillov model.
Yes, Kirillov model. Sorry, you're correct. Okay, so let me maybe say something that will give more intuition for what is going on here. So if I have a group G, then for just any group, forget about GL2F for the moment, just any non-commutative group, maybe finite, maybe not, I don't know, then there's a product of G modules given by the diagonal action. That is, if I have two G modules V and V prime, I can tensor them just as vector spaces, and G acts diagonally on this tensor. This is something that always exists, this monoidal structure, this multiplication, but it has very complicated interaction with irreducible representations, with the spectral decomposition of G. Yes, I can have elements that are in one place of the spectrum and spaces in another part of the spectrum. So I can have two very different irreducible modules. And when I tensor them, I get something which is usually not irreducible and decomposes into many other different irreducible representations. So, and this is a very interesting thing to do, and people study that. But generally speaking, this tensor product does not play well with the spectral decomposition. Now, if I have a commutative group G, then there's another way to multiply G modules, which is called the relative tensor product. That is, I take V times V prime over G. Now, this relative tensor product also carries a G action because G is commutative, so I can cheat and let G act just on either one of these spaces. And unlike the previous one, this product, this relative tensor product plays very nicely with the irreducible representations. Yes, if an irreducible representation for a commutative group is a character, and if I multiply two characters over G, then I either get 0 if they are different characters, or I just get the same character if I multiply a character by itself. And what is going on here is that basically the new product that I defined for GL2F, it acts very much like you would expect from this second case, from the relative tensor product in the commutative group case. That is, if I have an irreducible G module and another irreducible G module, and I take their Y product, then I either get 0, or I just get, or if V is generic irreducible, then I can just get V itself back. So somehow, this is maybe one way to think about this. This is a kind of spectral product of G representations that usually shouldn't exist for non-commutative groups. In other words, this is some kind of a categorical group structure on the dual of G. Maybe that's one way to think about this. So maybe, I'm not sure if this helped clarify things, but hopefully this did. Now, the next thing I'm going to discuss is that I have 8 minutes left, and I'm going to say just 2 words maybe about the...
Take your time. We are not so limited to 60 minutes strict. So if it takes a little bit longer, it's totally fine. We also ask questions, so there's no rush. Okay, so now, in any case, as you can see, I have a prepared slide here for just this moment, that the next thing I'm going to talk about is the global theory. The global theory deserves a whole lecture on its own, but this is not something that's feasible within... May I ask another question?
Sure.
So coming back to this new monoidal structure, you said this identity is 1y, yeah? So yes. So this requires a proof, I guess, yeah. And what is the proof here? What is the idea of the proof, and what aspect of the Weyl representation do you use?
It's so simple that you don't really have to use anything complicated about the Weyl representation.
Sorry.
So I'll just say a short thing about it because it's pretty simple, but because I can. Just if you have a Weyl representation, then it has an action. So it has this action of this extra hidden action, and the way it does is that if you have the unipotent radical, just upper triangular matrices, then they act by multiplying by an exponent of the determinant of the matrix times just an exponent of the determinant of the matrix. This is the action. And what happens when you take tensor product with this one with the Whittaker space? Then that's the same thing as taking the equivariant functions, taking a equivariant quotient with respect to some specific character on the unipotent radical. So this essentially what this does is that it restricts you to elements in M2F times F star in this case, such that the determinant of this element times the element in F star has some specific product. So if you have an element, so the subset of M2F times F star, where the determinant of the matrix times the element in F star is say equal to 1, then that's just GL2F. And GL2F and functions of GL2F is the identity factor, and that's everything there is to it.
Thank you.
So now, any other questions before I say some words about the global theory?
Can I ask again, just to clarify? So actually, your isomorphism of this tensor product of three things in the very beginning, before you started to introduce this triple action.
Yes.
Yes. Between this and V
yes.
is exactly the statement about the theta correspondence, the fact that the home from M2 to the pi times dual pi is isomorphic to pi, because that's how the correspondence for SL2, SO4 works.
Yes.
Okay. So in particular, this is an issue of like really small rank, right?
Yes. So this
you won't be expecting immediately to have any similar construction for any higher rank.
No, I don't know how to generalize the Weyl construction to higher rank. It's at the moment this is something that is a research problem. I don't know how to. I'm not. There are ways to try and do this. I have some approaches, but no concrete construction. This doesn't generalize easily.
Okay, thank you.
So, so let me say a few words about the global theory. Let's fix notation first. I have a global function field of characteristic node 2. I have the Adels, and I have the category of smooth GL2A modules. Now, unfortunately, I just said the category of smooth GL2A modules, but you guys should immediately have told me, what are you doing? This is the wrong category to consider. Because no one is actually interested in smooth GL2A modules. It's a huge category. It has everything. People only really care in the global setting about automorphic representations, which are a tiny, tiny subset inside this category. In fact, I said subset and not subcategory because it isn't even clear what it means for a representation to be automorphic. If you have an irreducible representation, we say that it is automorphic if it appears as a constituent in some space of automorphic functions. But that's basically all we know to say. Yes, first of all, it's unclear if this is, you should think of it as an extra piece of structure or if it's a property of the representation. And if you have a representation that's glued out of two irreducible automorphic representations, then it's not clear if you should think about the extension as also being automorphic. So I do have this category mod G of smooth G modules, but it's awful. It's not really something that you can work with. Now, for the moment, even though it's awful, let's just bear with me. Pretend that let's just try and see what we can say, and maybe we will be able to salvage something from here. So we have this symmetric monodal structure in the local case, and all of the constructions using the well representation, etc., they all very easily generalize to the global case. So you can just define you can give a triple action on functions on M to A times A star, and you can use this to define a bifunctor, where you take V, Y, V prime to be this tensor product of V and this space of functions and V prime. And this is again a symmetric monodal structure on this huge category mod G, and it has a unit which is the global Whittaker space. Now, so you can do all of this, and now here comes the magical part. So first of all, in the local case, we used, in our construction, what we did was that we used basically the theory of the theta correspondence. Yes, we used the well representation to take one kind of GL2 models into another kind of GL2 models. And the theory of theta correspondence actually has two parts. One part is a local part, which allows you to take models from here to models that are there using the well representation. And the other part is the theory of theta functions. What this theory does is that it gives you some specific construction of an automorphic function that if it is non-zero, then it tells you something. So it's beneficial to understand what happens in this case in the global setting. What does this theta function mean? What is the second part of the theta correspondence tell us here? So first of all, let's make a definition. Consider the space of automorphic functions. So functions on GL2A modulo GL2F that are smooth and compactly supported. And now let's consider just the generic functions. What do I mean by generic functions? I mean the functions on the automorphic quotient that are orthogonal to all one-dimensional characters. That when you integrate them across the determinant, you get 0. These are the generic automorphic functions. Now, if you take the generic automorphic functions, that's a subset of the automorphic functions, and you try to track down what the theta functional means in this case, then it almost boils down completely to the following statement, that there is a product, there's a canonical map given by a theta function from this, let's call this I, this space of generic automorphic functions, from the Y product of I and I to itself. There's just a map, a bilinear map with respect to this exotic symmetric monodal structure. And that's almost the entire contents of the theta functional in this case. Now, so we have this bilinear map that pops out naturally out of the theory of theta representation, of the theta correspondence. And well, if it's a bilinear, by now you shouldn't be surprised that this bilinear map turns out to be more than just a bilinear map. It is an associative commutative algebra structure. Basically, what this means is that you have a triple linear map that can be defined by composing this bilinear map with itself in two different ways. And these two triple products are the same. It means that there is a unit, which is essentially given by taking the Whittaker functions of an automorphic representation. That's basically the data that is the unit of this case. It's just a map from the Whittaker space into automorphic functions, which is dual to taking the Whittaker function of an automorphic representation. And that's really nice. So what happened here is that we have this algebra of functions. Now, once you have an algebra, there are other questions that you can ask. For example, you can take its category of modules. So if you have an algebra in a symmetric monodal category, you can consider the modules in that symmetric monodal category. These are objects inside mod G, so G modules or G representations, along with maps from I times M to M that satisfy some associativity and unitality requirements. And it turns out that so what I propose, or the name I'm going to give to this category of I modules, I'm going to call this mod aught, the abstractly automorphic representations. This is just some category of I modules. And what I propose is that this category is a category that you can think of, that you can try using as a replacement of, or that really you can think of as being a category of automorphic representations. Now, on its surface, this category looks like it's some extra data. Yes, if I have G module, then I need to add the structure of an I module to it so that it becomes an abstractly automorphic representations. But that's not actually something that I need to do. It turns out that if I have an abstractly automorphic representation and I forget the abstractly automorphic structure, I just remember only the underlying G module, then this map is fully faithful. This means that there is a unique way, any objects of mod G and G module can be extended to an abstractly automorphic representation in at most one way. So basically it's a property. If I have an object of mod G, either it is abstractly automorphic or it is not. In other words, I have a fully faithful subcategory. I've just selected some of the objects inside this huge category mod G. I selected just the ones that are compatible in some manner with I, and this select objects, the ones that can be associated, that can get an I module structure, are the ones that I propose calling abstractly automorphic representations. Now, this category has many nice properties. I'll just because we're basically out of time, I'm just going to list them. So as I said, it's just a property. So if you have an automorphic if you have a G module, then it either is or is not an abstractly automorphic. If you have an irreducible representation, then I've told you nothing new. That is, an irreducible G module is automorphic if and only if it is abstractly automorphic. So as I said, there's a definition that makes sense for being automorphic that makes sense only for irreducible representations, but this definition strictly generalizes it. It's consistent in the irreducible case. It has non-irreducible examples. For example, I, or just all of the automorphic functions as a space, as a G module is abstractly automorphic. So that's something that you would really expect out of such a definition, that the space of automorphic functions would be abstractly automorphic. It has excellent closure properties. It is closed under limits, colimits, subquotients, contragradients, anything that you might want to be closed under. And it has many more properties. For example, it turns out that this category of abstractly automorphic representations admits a decomposition into components that are cuspidal components and Eisenstein components. Just like in the local theory of p-adic representations, you have supercuspidal components and parabolically induced components, and just you can. There's an entire theory there that I don't have time to describe right now, but it's just that you can. That turns out it just works fine. Anything that you had wanted out of this category that I was able to formulate, I was also able to prove. So basically, I sprinted across this last mile here. It was probably utterly unclear and impossible to understand, and I apologize. In fact, I apologize in advance as well. But I would still appreciate it if you have any questions. And
thank you very much. That was a very nice talk. So indeed, if there are any questions.
Can I ask a question about this abstractly automorphic? So can you give some characterization of when irreducible representation is abstractly automorphic, kind of independent of this Whittaker thing and so on?
So I can give a definition that's independent of the multiplicative structure. You can just define this in a non-multiplicative way. As it turns out, there's a map from the Whittaker space to the space of automorphic functions. It's just it's the map, and the image of this map is exactly this I. So there's a map from Whittaker space to I as a subspace of automorphic functions. This is the map that's dual to taking Whittaker models. And now the thing is that if you one way to characterize being abstractly automorphic is that there's a map from V this symmetric structure 1. So the map from V times 1 to V. It's isomorphic. Yes, V times 1 is always isomorphic to V. And so what happens is that if this map from V times 1 to V factors through V times I, then that means that it is abstractly automorphic. So it means basically that if you take this whale lift with Whittaker functions, then you get the same, you get your original model. But if you can do this in a way that factors through automorphic functions, then you are abstractly automorphic. This probably isn't what you wanted to hear, but.
I thought maybe something naive, like everyone who appears in some spectral decomposition of the space.
So the problem is that appearing in a spectral decomposition of the space is some property of irreducible representations. Yes. For example, if I take an irreducible automorphic representation and I add it to itself uncountably many times. Yes, I take a huge dimensional space just by taking an automorphic representation and adding it to itself as many times as I want. At some point, this cannot appear in any kind of reasonable.
Yes, I meant only for irreducible representation.
No, for reducible representations, it's exactly the standard definition. For reducible representations, this reduces to being a constituent of the space of automorphic functions. This is all it means. For reducible representations,
but a general representation is abstractly automorphic if and only if all irreducible subquotients are abstractly automorphic.
No, it's very easy to see that not just if you take, because just even for GL1. Yes, you should think of this like a closed subset in an algebraic space. You have something that's supported on this closed subset, but if you have two of them, the extension might not be. This isn't closed under extensions. You can take
it's not closed.
It's not closed under extensions, only under limits, colimits, subquotients, and contragradients.
Okay, thanks. You said it's closed under everything we want.
No, but you shouldn't want this.
Okay, thank you. Yes.
So I was a bit confused about the space of functions of compact support. So for example, if you have a cuspidal form on GL2, you only know that it is rapidly decreasing, right? Not.
So this is the p-adic setting. Yes, I'm working over a function field.
Okay, you didn't say that. So what you are talking about is only for okay, yeah, I see now. Thanks. So it's only function field. Okay.
Yeah. So probably there is some theory that also works for arithmetic fields, but just that would mean I would have to figure out the specifics of the Archimedean case, and I didn't do that. So I'm not claiming anything about it, but I suspect that everything that I said here about this category should work more or less the same, but you need to properly account for the Archimedean places and the topology, and you probably need to introduce some topological vector spaces or some analogs of them, chronological vector spaces, something like that.
So the analog would be just everything subspace of automorphic forms orthogonal to one-dimensional representations.
Yeah, so you would need, instead of compactly supported, you would probably need Schwarz functions. Yes, rapidly decreasing smooth functions, blah, blah, blah.
I'm thinking.
Is there further questions? Maybe then I ask a stupid question. So say for an Archimedean field, I mean, we know that we can, for instance, multiply modular functions, yeah? One of weight K with weight L, and we get, is it something like that as you would obtain when you have a monoidal structure and automorphic representations?
So for modular, sorry, can you hear me?
No, I find it's only my internet connection is very unstable, and sometimes I'm out. So this is probably on my side, yeah. So I can't hear you all the time. But please continue.
To my understanding, what you asked is that how is this multiplicative structure related to the multiplication of modular forms, which is another kind of multiplication that exists. Now, I would answer to that with this slide here that I gave the example of that there are two kinds of products over general groups. For general groups, you have this diagonal product, which badly interacts with irreducibles. And you also have this relative tensor product that exists only for commutative groups, which respects the spectral decomposition. So the product that you are describing of multiplying modular forms is something that's related to the world of this top kind of product, of this this product that doesn't respect the spectral decomposition. The multiplication that I'm proposing is something that comes out from the world of this other kind of product, the relative tensor product that respects the spectral decomposition. So if you multiply two modular forms, you get a modular form that's very, very different. It's completely different irreducible representation. On the other hand, if you take with this algebra structure of I, if you take the part of I that corresponds to some irreducible representation and the same part, then you once again fall into the same part. So this respects the center of this respects the Hecke operators essentially. This product. So does this answer your question? Probably it looks like so. It looks like your connection dropped out probably. So I'm okay.
I think we have lost Bernard for the moment. Are there any other questions? Does not seem to be the case. So let's take a break. Maybe we continue at past, so in 16 minutes or so.
Thank you very much. It's been an honor.
Thank you very much. It was a very nice talk. So Amos, should we try to see if your sound is working and whether your share screen is working and so on?
Yeah, can you hear me now?
I can hear you perfectly, actually.
Okay, good. And so I'm just going to share the screen.
Yeah, let's see if that works.
Give this a try. Okay, so right, this is it. Okay, so, and I'm going to take it to full screen. Is that what I'm supposed to do?
I think so, because at the moment it's a bit small.
Yeah. Okay.
Yeah, this looks great.
Okay, good.
Very good.
So let's start with beginning. Okay. Okay, so we're all set, right?
Then we're all set. So I will.
Good.
So Jessica asked whether the slides can be on the website. So some people like to sort of be able to go back in the slides. So if you're okay with that, I can put them already on the website.
Sure, go ahead, no problem.
No, then you have to send them to me first.
Okay, I'll send it to you right now. Yeah, of course, there's the issue that I'm not sure if I'm actually going to get to the last slide, but that doesn't really matter. There could be, okay.
So I'm going to unshare the screen for now, because then people can see each other again and I can see.
Sure. Okay, good. Let's see. Where am I? No, just 1 second.
Sure.
Okay. And it's gonna be okay, PDF. Diophantine approximation on reductive homogeneous spaces. Okay, good. It's a little slow, but I'll send it to you in 1 minute. Actually, you know, sometimes people prefer the slides to be, well, okay, it doesn't matter. Maybe I'll send you later the slides in a kind of a preprint form.
Oh,
But
that would be very nice, yes.
Yeah, it doesn't matter. For some reason, it's taking a long time to upload, although it's a very small file. Okay, it should be here. Well, why is it not uploading? I don't know. It's still waiting for it to upload. It's very strange. Maybe it's better to try again.
So the problem is the email program?
It's a very small file, but for some reason it only uploads half of it. It's very strange. It's just a very small PDF file. I don't know why it would.
The mysteries of life.
If you send it by email, it will be faster.
No, it is by email.
Or
It's
you
a
can
separate,
share it by chat.
By
the chat here in the Zoom.
I'm not sure. I'm just trying to send it by regular email.
Yeah, so the alternative would be that you upload it into the chat of Zoom. So there's a way to put a file in there as well.
Yes. Okay, maybe now it's going. I don't know. I've never had this happen to me. It's such a small file. Yeah, I'm not sure how to upload it into the Zoom chat. Maybe it's very easy. Okay. Well, let's see if you get it.
Yes, there it is. Okay, very good.
Okay, so I'll be right back.
Okay.
Okay, I think it's about time to come to our last lecture. So please stay with us. I mean, if you want to be on the group photo, we do it right after the discussion of Amosh's talk. So as we decided, I mean, for those of you who want, I mean, we can put on it. And we want to make a nice poster and postcards, which we can then send to all of you, and then you might have a nice souvenir. We hope that the resolution will be fine. I mean, Job was that we actually can recognize ourselves there. Okay, but that said to be that, so now we welcome Amos Nebo from the Technion in Haifa, and he kindly agreed to talk to us and explain to us some Diophantine approximation on reductive homogeneous basis. So please, Amos. I think you have to share screen now. And
okay, is the screen visible? Am I being heard?
Yes, the sound is good, and
yeah,
the
screen is
visible.
okay? Okay, great. So let me start, first of all, by thanking the organizers, Job and Bernhard, for organizing this Zoom virtual meeting. It's very good to keep in contact with people and learn about what people are doing in these very isolated days. So I'm very happy to give this talk. And what I decided to do is really give a kind of an invitation for a certain collection of problems, which I think are quite interesting. It's a blend of arguments or, well, problems in ergodic theory and dynamics, and unitary representation theory, and the theory of algebraic groups. So I hope people here will be interested in this collection of problems. And I would like to mention, of course, that everything I'm going to talk about is based on joint work with Anish Ghosh and Alex Gorovic. So let's start by formulating the following problem. Okay, something is wrong. Okay. So we're going to consider the general setup of homogeneous spaces. So let G be a non-compact, locally compact second countable group. And gamma will be a discrete lattice subgroup of G, so that the coset space G mod gamma admits a G invariant probability measure. This also means that G is unimodular. And we let H be a closed non-compact subgroup of G. And below H will also be unimodular. So G modulo H has a G invariant measure. This is not necessary, but we're not going to talk about the non-unimodular case in this talk. It involves a lot of overhead. And we assume that almost every gamma orbit in G mod H is dense. And in fact, in everything we're going to do below, gamma will in fact be ergodic on G mod H, which of course implies the previous condition. And we will comment on the fact that this assumption is very, very common. It's a very, very common assumption, very easy to satisfy. Okay, now we denote by norm G a suitable gauge on G, which I'm not going to define more, but it's going to be obvious in everything we do below. And we let rho be a suitable metric on the homogeneous variety X equals G mod H. Once again, I'm not going to specify the properties, but we will have the obvious choices in every case. And what we would like to do is to consider approximation on homogeneous spaces. Namely, we would like to analyze the efficiency of approximation by gamma orbits on the homogeneous space X equals G mod H. And to give this, and we give this a very precise meaning as follows. We fix X in X, and we suppose that for all X0 in X, and for all epsilon less than epsilon naught sufficiently small, we can solve the inequality that says that the distance between gamma X and X naught is less than epsilon, meaning in particular that the gamma orbit of X is dense in X, in the homogeneous variety, and subject to the condition that gamma in gamma has norm or gauge, which is bounded by a constant time 1 over epsilon to some power zeta. And so we are interested in approximating with this, we might call it a polynomial bound on the norm of gamma. And here epsilon naught, zeta, and b depend on the pair, the way we set it up, depend on the pair XX naught. And so we can say that zeta XX naught gives the rate of approximation of a general point X naught in G mod H by the gamma orbit of X. And having done that, we can certainly go one step further and define the approximation exponent kappa XX naught as the infimum of zeta XX naught, such that the foregoing inequalities have solutions satisfying the bound stated above for all sufficiently small epsilon. So this is the tightest the most efficient exponent that one can have for this approximation problem. And so now what we would like to do is to quantify this exponent, which I'm sure everybody agrees quantifies the denseness of the gamma orbits. So the first problem would be the problem of finiteness, obviously. So we should determine when does there exist a finite constant zeta, which depends on gamma and the homogeneous space G mod H, which bounds the rate of approximation by almost every lattice orbit. That would certainly be a nice thing to have. And actually, going a step further, we would like to determine when does there exist a finite uniform bound for every lattice orbit, without any exceptions. I introduced the almost sure context right at the beginning, but you might be interested to know whether, in fact, there are situations where one can have a statement for every orbit and every orbit is dense. And the answer to that is yes, it is possible and it happens. It doesn't happen always, but it certainly happens in many interesting cases. And having established the finiteness, we would like to establish some explicit bounds, namely an upper bound and a lower bound for the rate of approximation. And we would like to explicate their dependence on G, H, and gamma explicitly. And finally, and this is quite challenging, we would like to consider the problem of optimality. And by that, we mean to formulate a simple and easily verifiable, widely applicable criterion for when the upper and lower bounds coincide. And that would give rise to the optimal rate of approximation by lattice orbits on the homogeneous space. Okay, so what I would like to do now is to give a context to this general problem and try to demonstrate that it really is both very natural and at the same time, it encompasses many, many cases. or many, many examples. So the first example we're going to consider is integral Diophantine approximation on affine homogeneous rational algebraic varieties. And for this context, we have G, the real points of an algebraic subgroup of S and N are defined over Q. Gamma is a lattice subgroup of GR, for example, the lattice of integral points GZ in GR, but that's not absolutely crucial for this, for our purposes. But let's continue with that. And we consider the affine rational subvariety X in Rn, which is invariant and homogeneous under the G action. And so this variety is necessarily homogeneous space, X equals G mod H. And we assume all the assumptions that we had before. Let's say, so G is unimodular, H is unimodular, both of them are non-compact. So, and now we choose norms on Rn and MNR and restrict them to X and to G. So here we have our gauge and our metric, and they are the obvious choices. And then we consider the Diophantine inequality. The norm of gamma X minus X naught is less than epsilon, with gamma being an integral matrix satisfying the norm bound. The norm of gamma is less than or equal than B epsilon to the minus zeta. And the Diophantine approximation exponent kappa, which is the infimum of zeta. So this is an instance of the general problem that we mentioned before in this specific case. And now, one thing I should say immediately, given all of our choices, in particular the norms and this linear context, the exponent kappa x naught is in fact a gamma times gamma invariant function on G mod H. And because, well, maybe I will justify this a little bit more, but because gamma is going to be ergodic on G mod H, a gamma times gamma invariant function on the product is almost surely a constant. And so we do have a number, one number, and not a function, well, okay, a constant function of the pair x naught, which if we establish that it is the exponent, then we have what one might call the almost sure Diophantine approximation exponent on this variety. Okay, now, as everybody knows, there are many, many, many interesting homogeneous affine varieties defined over Q. And let's go through a few examples. So obviously, we can consider the unit sphere, and we can consider the one-sheeted hyperboloid, and we can consider the two-sheeted hyperboloids, and we can consider the variety of unimodular matrices. And we should notice that not all of these examples fall into the previous context. For example, in the case of the unit sphere, this is a compact variety, a compact homogeneous space. And in the case of the two-sheeted hyperboloid, the stability group H is in fact compact. On the other hand, the one-sheeted hyperboloid and the variety of unimodular matrices both have, well, okay, I mean, at least the variety is non-compact, but the stability group in this case is in fact the trivial group. We can consider general rational quadratic varieties and the varieties of orthogonal matrices, affine spaces. But I should mention that the way we consider affine spaces here, of course, is as a homogeneous variety, namely we think of affine space as the affine group modulo the linear group. Okay, the affine group modulo the linear group can be identified with affine space. And we have more general reductive group varieties, principal homogeneous spaces, symmetric varieties, spherical varieties, and much more. And in this context, one should mention a very, very beautiful and, in fact, I would say, deep problem with long historical roots, which is Lang's problem, which we like to call the problem of intrinsic rational Diophantine approximation. So this is a problem that Serge Lang raised already almost, well, I don't know, 55 years ago in his 1965 report on Diophantine approximation. Lang raised the problem of establishing the Diophantine approximation properties of typical points on rational homogeneous algebraic varieties embedded in RD. And his context was that you want, just as in the case of R, or the plane, or RD, you seek to approximate the general real point by rational points. So Lang proposes that you should study the problem of approximating the general real point on a rational homogeneous algebraic variety by the general rational point. And Lang raised specifically the problem of establishing an analog of Dirichlet's principle, which in our context, we actually identify with the problem of establishing an exponent of Diophantine approximation, just like we had before. And he raised the problem of establishing an analog of the famous Khinchin's theorem, and also an analog of the theorem of Wolfgang Schmidt, which was then very recent, which establishes a solution counting theorem. Of course, these three results that I mentioned just now, in the case of in the Euclidean space, in the case of Euclidean spaces. So Lang proposed to generalize this to general homogeneous rational varieties. And to emphasize this point, the approximation process is allowed to use only rational points on the variety itself. And so that's why it's natural to call it intrinsic rational Diophantine approximation. I'm going to make this distinction, namely, I'm sure all of you are familiar with the fact that there is a large literature of trying to approximate points on a variety which is embedded in RD by all the rational points in RD. For example, the approximation of curves in the plane and various other classical problems of this type. But the problem we're talking about here is really different. We are only considering rational points on the variety itself, namely intrinsic approximation. So going back to our examples, well, maybe I'll, okay, so, Lang's problems have the following concrete formulation. We consider an affine homogeneous algebraic variety X defined over Q, namely an affine variety acted upon transitively by a linear algebraic group defined over Q, and let XR be the set of real solutions, and XQ the set of rational solutions. So we would like to analyze quantitatively the system of intrinsic Diophantine inequalities that say that the norm of the real, the norm of the difference between the real point and the rational point is less than epsilon, and subject to the usual condition in Diophantine approximation that the denominator, the reduced denominator of the rational vector is bounded by some power of 1 over epsilon. epsilon to the minus kappa. So here x is in the real points and r is in the rational points, and dr is the reduced denominator. And just to recall, if r is a rational vector given by pi over qi, with pi over qi reduced fractions, then the reduced denominator is the least common multiple of these denominators. So this is a concrete, explicit formulation of Lang's problems on algebraic varieties. And now, of course, every affine rational variety has a dense set of rational points. But may, of course, have only a discrete set of integral points. For example, we looked at the unit sphere. Obviously, and we also looked at the two-sheeted hyperboloid, which is the same thing or can be identified with the upper half plane, Riemannian symmetric space, where the integral points are discrete. Integral approximation is not meaningful in these spaces, but Lang's problem definitely is, because both of these spaces have a dense set of rational points. And so therefore, we consider a natural generalization of Lang's problem, which includes both integral and rational Diophantine approximation, and which comes up in several important applications. I want to emphasize this point that the problem we're going to formulate is not just some, I don't know, something motivated by mathematical generality or, I don't know, completeness or something like that. It's motivated by some very, very important applications. Maybe I'll mention one in just 1 minute. So we consider intrinsic Diophantine approximation on a rational homogeneous variety by a constrained set of rational points, constituting a proper subset of the set of all rational points on the variety. Of course, a proper subset which is still dense. Okay, now the simplest example is to approximate using the set, for example, x z1 over p, consisting of rational solutions whose denominators are restricted to be powers of p, where p is a prime, or more generally, we can consider solutions using rational points with constrained denominators, the denominators being one of those, multiples of these different primes. And so, for example, one problem where this comes up, and historically, it has been one of the main motivations of this whole subject, and certainly it motivated myself and I believe my collaborators as well, is the famous Lubotsky-Phillips-Sarnak construction, where they use precisely matrices with entries in Z1 over P for their approximation process on the unit sphere and the orthogonal group. If you're familiar with the recent work of Sarnak and his and some collaborators on what Sarnak calls the Golden Gates problem, which again has to do with approximation in the unitary group, then once again, the main issue, the main event is really about approximation by constrained denominators. You cannot approximate by integral matrices and you're not interested in approximating by all rational points because you're interested in a finitely, in approximating a group which is finitely generated. Okay, so now what I would like to do is to say that, to connect it to what we said before, that we certainly have here a very large set of approximation problems, whether you prefer p-adic numbers or whether you prefer rational numbers or whether you prefer integers. But what I'm going to say now is that all of these problems, they all are instances of the problem we set out in the first slide. Intrinsic Diophantine approximation can be viewed, or it can be viewed as lattice orbit approximation problems, at least in many cases. So the gamma orbit approximation problem on a homogeneous space X equals G mod H, formulated initially, encompasses all of the examples considered above as follows. The integral Diophantine approximation we mentioned, we have the algebraic group HR in GR. These are two real algebraic groups defined over Q, both unimodular and non-compact. And gamma is the lattice of integral points. Here, X equals G mod H is a non-compact affine rational variety with an invariant volume form. Then we have p-adic integral Diophantine approximation. Now here, we're going to take G to be a product group. Maybe the notation here is not ideal, but here I take some algebraic group and take the real component and the p-adic component, and my group G now is this product. My subgroup H now is one component of this product, namely GQP. And so we assume, of course, that it's isotropic. G, the algebraic group, is isotropic over the p-adic field. And then we have the lattice, which is the group of rational points with coordinates in Z1 over P. This is an irreducible lattice, and our homogeneous variety is simply GR modulo GQP, so it's just GR. It's just GR, a possibly compact rational variety. I mean, the sphere and the orthogonal groups are perfectly fine here. And in this particular case, it's a group variety, but of course we can make it into a compact homogeneous space. And so the problem we have here is simply the problem of the dense subgroup gamma, dense in GR, acting on GR simply by the usual group multiplication. This is the approximation problem that we have here. This is a very natural approximation problem. We'll have some examples a little bit further down. And then we have an intermediate case, the integral Diophantine approximation. S is a finite set of primes, G is an S algebraic Q group, and H is an isotropic S algebraic subgroup. And gamma, the group of rational points whose entries are in this ring, is an irreducible lattice. And finally, Lang's original problem is the problem of rational Diophantine approximation, is the case where we consider GA and Edge A to be algebraic groups of rational adels. To be on the safe side, one wants to assume the G is simply connected, because otherwise the overhead is really quite formidable. And then gamma equals GQ is the lattice subgroup of rational points. And so all of these examples, they really amount to the same thing. It's the approximation problem for lattice orbits on a homogeneous space. Okay, so this is the general problem that we would like to consider. And of course, once you put it in this way, then of course, the natural context for intrinsic Diophantine approximation on homogeneous varieties to consider includes arbitrary affine homogeneous varieties for linear algebraic groups. And they may be defined over an arbitrary number field. The rationals were really only just an example. Using k rational points constrained by an arbitrarily prescribed integrality condition on their denominators, so to speak. This constraints may be finite in number, and in fact, actually, they may be infinite in number also. And one would like to achieve simultaneous Diophantine approximation over several completion of the field K. And hopefully you want the approximation rates to be given by explicit exponents. So this is, I would say, a fairly robust collection of problems. And obviously, some assumptions are going to be necessary. So in what I would like to do now, then I would like to explain some of the results, specifically for the computation of the integral Diophantine approximation on real affine varieties defined over Q, where we have been able to obtain some solutions to the problem we originally formulated above. And so the first thing that we are going to have to do is to describe a lower bound for the integral Diophantine approximation exponent. Now, how are you going to approach this problem? So a basic ingredient in solving the Diophantine inequalities, which approximate a point x naught in X, is to estimate, first, to estimate how many orbit points gamma x are available to you in a compact neighborhood omega of x naught in the homogeneous affine variety x equals g mod h. If you're going to claim that points are getting denser and denser and you can approximate x naught at a certain speed, it'll be very useful to have an estimate of how many points do you actually have. And so define the empirical growth parameter of such points. We denote it by A. And it is the supremum over all omega compact, omega contained in G mod H, of the lim sup of the log of the number of elements gamma in gamma, such that their norm is less than t, and they actually take x to omega. Omega, we think of it as a vicinity, as a neighborhood of x naught. And we normalize this by log t. So this number definitely exists, whatever it is. And now let's see what we can say about this number. So heuristically, of course. And so let age t be the norm ball in age. I take the norm on G and I consider age in age whose norm is less than t. So if I take x to be, for example, the identity coset, the coset of age, the coset consisting of age, then these orbit points that we see here, the orbit points that we see here, gamma x is in omega, these orbit points are those points in a set gamma intersect omega times age, whose norm is at most t. Namely, the norm of gamma is at most t, and gamma modulo age is in fact in omega. gamma x is in omega, where x is E in this case. So it follows that their growth, the growth of the number of points, obeys the bounds which are satisfied by the volume growth of norm balls HT in the stability subgroup H. So the point is that the orbit points that I'm looking at, they deposit the orbit in a neighborhood of H, in a neighborhood of H, in the set omega times H, where omega is some compact neighborhood. And so they really, so to speak, only grow in the H direction. And so this collection of lattice points, which, so to speak, only grow, are only allowed to grow in the H direction, their number is in fact comparable to the volume of balls in H. And that is a form of the lattice point. It's a kind of a pretty, well, it's a form of the lattice point counting problem in this case. But it shows us the absolutely crucial point that the number of points available to us for approximation, the number of points that actually play this game, is controlled by volume growth in the stability group.
May I ask a question?
Yeah.
This A depends on X, right? Or is it independent of X?
No, it does not. It does not. I mean, it does not. X is a fuzz here, as you can see. I have the eta. So the A is independent of X.
A is independent of X. Okay.
A is independent of X. I formulated it to have some fuzz, as you can see. So the number of points available for the approximation, therefore, it's going to obey the bound that these points, gamma and gamma, such that the norm of gamma is less than T and gamma X is in omega, is at most T to the A plus eta. And now we have another ingredient. We recall that G and H are unimodular, and we assume that the local behavior of the invariant measure mx on x is given by, well, the volume of a small neighborhood, x minus x is less than epsilon, is some power of epsilon. And of course, this is certainly the case when x equals G mod H is a real affine variety, and D here is nothing other than the dimension of the variety. And so in this compact neighborhood omega of x naught, there will exist an epsilon separated net of size roughly epsilon to the minus D. This is a fact we're all familiar with in Euclidean space, or, well, a manifold, or a compact neighborhood inside a manifold. And that means that there are at most T to the A pigeons, namely points of the form gamma X and omega, whose norm is less than T, roughly epsilon to the minus D pigeonholes, namely epsilon balls in omega. And so if the Diophantine approximation omega is to be successful, then clearly you have to have more pigeons than pigeonholes. And so T to the A at least epsilon to the minus D. And so that means that T is at least epsilon to the minus D over A. And we can conclude that D over A is a lower bound on the Diophantine approximation kappa. It's impossible to approximate points on X equals G mod H as above by points in generic lattice orbits any faster, namely lattice of small size. Of course, it's important that this statement is generic. It could be that some specific orbits are much better, but you cannot, for a generic orbit, obtain the bound which is less than d over a. So this is a very simple number. It's just the dimension divided, the dimension which is a proxy for the volume in our case, divided by, well, the rate of growth of the number of points in the lattice, in the relevant points in the lattice. So this is a pigeonhole lower bound. And this is a very general statement. You can see that I really used only some very specific, well, just just the estimate t to the a and the behavior of the volume. So now we would like to talk about deriving an upper bound. And now an upper bound on the Diophantine exponent requires completely different considerations, which might be more familiar and maybe more interesting here. And they would depend greatly on the various ingredients that we have here, G, H, gamma, etc. So these considerations are first, spectral estimates in the automorphic representation of G on L2 G mod gamma. But, and this is maybe the absolute key point here, the spectral estimates restricted to age. I'm going to emphasize this for the rest of my talk. The spectral estimates in the automorphic representation of G on L2 G mod gamma are viewed from the eyes of age, namely the representation is restricted to age. And these are going to lead us to an effective mean ergodic theorem for the action of age on the probability space G mod gamma. I'm going to explain this a little bit. And we're going to be using some dynamical arguments utilizing the speed of equidistribution of age orbits in G mod gamma, which is a consequence of the mean ergodic theorem. And the dynamical arguments are going to use them in the form of a shrinking target argument, which is a well-known argument in dynamics. And finally, we're going to use an effective duality argument. And this is another key to this analysis. The effective duality argument translates a rate of equidistribution for the age orbits in the action of age on G mod gamma to a rate of approximation of the gamma orbits in the action of gamma on G mod H. The duality principle is, well, the duality principle may be, well, definitely one of the most fundamental tools in homogeneous dynamics. And you can view what I'm saying here as essentially giving an effective form to the idea of duality in some instances and exploiting its properties. Duality meaning the recipe of duality means if you want to understand something about the orbits of gamma on G mod age, it'll be very useful for you to analyze the orbits of age in G mod gamma. So in homogeneous dynamics, this is really an axiom, but actually I think it's very common also in other problems in geometric analysis on homogeneous spaces. Okay, so let us start with these ingredients, and we're going to start by the effective mean ergodic theorem. So to formulate our spectral estimate, we consider the intersection of norm balls with a stability group once again. HT is the set of elements in A norms less than T. And we do the environment measure on G mod gamma, and now we define averaging operators, pi y beta t. These are operators acting on L2 G mod gamma, and they have a very, very natural definition classical object in ergodic theory, they're given as follows. If you have a function f in L2, then you consider the values fy h, namely you translate your point by all the elements age in ht, and you average the values of f, and then you normalize by the measure of ht. If you are familiar with the ergodic theorem or the ergodic averages for the case of flows, for example, where the acting group G is simply the real line, then you will recognize this as the standard ergodic averages on intervals. So this is a very natural generalization. It basically measures how the orbit of Y distributes itself in the homogeneous space. You filter the group by HT, and then you look at how well do you average. And now we're to assume that the quantitative mean ergodic theorem, the averaging operators, pi naught Y beta T holds, namely, that there exists a positive theta such that if you consider your averaging operator, pi y beta tf, and you subtract the so-called space average, namely the integral over y of fdm, then you get a really good result. And what is this good result? You have that the averaging operators converge to this constant, the integral of y over y of fdm, a constant. This is known in ergodic theory as saying that the time averages converge to the space average, but the convergence is very special. In fact, you have a rate for this convergence, and the rate is like the volume of HT to some negative power theta. This is a very remarkable inequality, and it doesn't really exist in classical ergodic theory. This is a feature of semi-simple representation theory, or yeah, I think this would be accurate to say. It can happen for groups which also, say, have a radical, but the root of this operator norm inequality is the unitary representation theory of semi-simple groups, as we will talk about in a minute. Okay, so we have this operator norm estimate. This is our effective mean ergodic theorem. And so you, of course, might be skeptical and say, well, you know, maybe this is too good to be true. But actually, this estimate holds in great generality. And what underlies this estimate is that the representation of G in L2 naught, zero integral functions in G mod gamma, typically has a spectral gap. So I'm sure everybody here is very familiar with that. And now, in that case, if you have a non-amenable unimodular closed subgroup age in G, well, typically it will also have the property that the unitary representation of age in L2, I guess I switched it, L2 naught has a spectral gap as well. This is a very simple fact. The age a non-amenable age inherits the spectral gap. And for example, if age is any non-compact simple subgroup of G, then the spectral gap for age implies the estimate stated above on the operator norm of pi y beta t. So this is a fact that I think most people are very familiar with. So the fact that you know that there is a spectral gap for a simple group, let's say, it has an implication for the decay of matrix coefficients in a uniform way. And if you have a uniform decay from the matrix coefficients, then you really shouldn't be surprised that you get a operator norm estimate. And so this is designed to make it plausible that the effective mean ergodic theorem is actually very, very common. And so H does not have to be non-compact simple. There are many. Once you begin to have spectral gaps, then you have them in many other situations. And so the effective mean ergodic theorem for the averages beta t was established in 1998, and it was elaborated further in joint work with Gorodnik. Maybe I should say, although I'm sure everybody realizes this, that if you have the mean ergodic theorem, then it's a one-line exercise in ergodic theory to show that it follows that H is ergodic on G mod gamma. And then it's a standard argument by the duality principle for homogeneous spaces that the ergodicity of gamma on G mod H follows. And so in particular, almost every gamma orbit in X equals G mod H is dense. This was one of the assumptions on the first slide. Okay, so now we're finally ready to formulate our upper bound. So G in SLN R is an algebraic group defined over Q, H a closed algebraic subgroup, both unimodular and non-compact, and gamma a discrete lattice in G. Yes. And so the rate of growth of lattice points in the norm balls HT is the same as the rate of volume growth of HT, namely T to the A. This is one ingredient. A second ingredient is that D equals the dimension of the variety, and that controls the local behavior of the volume on the homogeneous variety. We assume that the averages supported on HT satisfy the quantitative mean ergodic theorem to G mod gamma with rate theta. This, of course, implies that G is a non-amenable group. I'm sorry, H is a non-amenable group, and certainly G is a non-amenable group. Just in case you were wondering about this, we say nothing in this theorem about, I don't know, abelian groups or unipotent groups or anything like that. And now we have the following result. Under the assumption stated above, the Diophantine exponent satisfies the upper bound, that kappa is D over A, the same D over A that we had before, but it's being corrected by some number 2 theta. The theta is the rate in the mean ergodic theorem. And so the conclusion is that if 2 theta equals 1, then the lower and upper bounds for the Diophantine exponents coincide. Okay, so what does that mean? If we go back to our mean ergodic theorem and we pay attention to the fact that 2 theta equals 1, if and only if theta equals 1/2, then we see that the rate of decay in the effective mean ergodic theorem is 1 over the square root of the volume. 1 over the square root of the volume. And of course, this is not going to, what I'm going to say now is not going to be a surprise for all the people here in presentation theory. Let me repeat it. If the rate of convergence in the mean ergodic theorem for the averaging operators beta t acting on L2 naught G mod gamma is as fast as the inverse of the square root of the volume of HT, then the rate of Diophantine approximation of gamma orbits on the variety X equals G mod H is best possible, and given by kappa equals D over A, the a priori pigeonhole bound. And this is again, okay, this is going to be very familiar to everybody here. If the stability group is H is simple and non-compact, And the restriction of the automorphic representation by not Gmod gamma to H is weakly contained in the regular representation of H, then the Diophantine exponent of the irreducible lattice gamma in G in its action of G mod H is best possible and is given by K equals D over A. And so corollary 2 is just a reminder for all of you that this being weakly contained in the regular representation for a simple group means that the representation in questions are tempered. And when the representation in questions are tempered, then the matrix coefficients obey the best possible decay bound, which is, well, in this language, 1 over the square root of the volume, essentially the rate of decay of the Harishchandra-Xi function. And the fact that weak containment in a regular representation implies the norm estimate given by the parameter theta equals 1/2 in this case is therefore a reflection of the Kunze-Stein phenomenon, which gives you an operator norm estimate given your spectral information, or being weakly contained in a regular representation. And so, having said all that, maybe some of you may be very skeptical that, I mean, temperedness is well known to be, well, temperedness is a very, very high bar. I mean, for example, if you want to show that G is tempered in L2 G mod gamma, okay, this is very, very difficult. And in the case of SL2, for example, some of the hardest problems in number theory depend on it. So this may look like a result where one can be very skeptical about. And so here we come to maybe to the main point of this analysis, to show that G is tempered in L2 G mod gamma is very difficult, and it is actually usually false. But it's a very remarkable property of unitary representation theory of semi-simple group that it's often, and sometimes you can say even generically, the case that while G is not tempered in L2 G mod gamma, a subgroup of G actually is. And this is a very surprising and useful fact, that the foregoing optimal spectral estimate for H holds in considerable generality for a large class of triples, GH gamma with H a non-amenable group. And I have 3 more minutes, so let me give you a few examples. So let's define the condition H is tempered in G mod gamma if the unitary representation of H in G mod gamma is weakly contained in the regular representation of H. And let's define the condition H is tempered in G if the restriction of any irreducible non-trivial unitary representation of G to H is weakly contained in the regular representation of H. This implies, of course, that H is tempered in gamma G for every lattice gamma. And there are several general principles which can be used to establish subgroup temperedness for a remarkably wide variety of cases. The granddaddy of all of these arguments is Kazhdan's argument. Kazhdan in 1967 actually proved that when you consider H to be SL2R semi-direct R2, and it is contained in G, some algebraic group G, for example, SL3, then any unitary representation of G without R2 invariant unit vectors is tempered when restricted to SL2. I'm sure everybody here remembers the proof. Okay, it's a very, very elegant argument. It's not really very hard, But that is the origin of Kazhdan's property T. But it's a kind of a remarkable thing that there was an enormous amount of attention paid to Kazhdan's property T. But the estimate that Kazhdan proved in the original argument was actually that the restricted representation is tempered, not just that it had a spectral gap. So that is one, this is maybe, well, I don't know, definitely one of the first arguments along these lines. Now, let G be a simple property T group and H a semi-simple subgroup. And so then there are universal pointwise upper bounds on the matrix coefficients of G in general unitary representations. A very well-known fact to everybody here, the theory of matrix coefficients of simple groups. And so you can take these universal pointwise upper bounds and simply restrict them to the subgroup H. It's a function on H. It's the matrix coefficients along H. And it may well be the case that when you restrict them to H, they are in L2H, L2 plus epsilon H. And so the representation restricted to H is a tempered representation. It's weakly contained in the regular representation of H. So that you sort of have to see in order to believe. The argument itself is completely elementary, but maybe you think it's very rare, but it's not. For example, L2 plus epsilon integrability for restrictions holds for the images sigma and H of all the irreducible finite dimensional representations sigma n of SL2R into SLNR, at least 3, and this was observed originally by Maris for the purposes of argument. But in fact, if you think about it, this can be greatly generalized. For example, given a simple group H and for example, SL3 or SL4, and an irreducible finite dimensional representation sigma of H into SLNR where n is large, well, sigma H is then going to be a tempered subgroup of SLNR if the representation sigma has sufficiently large and generic highest weight. And that's not very difficult to show. And another point is about tensor products. So, okay, I'll take another minute and then I'll be done. So irreducible non-trivial unitary...
Just take your time. I mean, you don't have to rush. There's time. If it takes 5 more minutes, it's completely fine.
Okay. So thank you very much. Okay, I'm going to try not to overstay my welcome. Okay, so irreducible non-trivial unitary representations of simple groups have matrix coefficients in L2kg for some k. So if you take a high LP, then it's okay. And restricting a representation of the direct product group G to the power k copies of G to the diagonally embedded copy of G yields then matrix coefficients which are in L2 plus epsilon. And so therefore the diagonally embedded subgroup G is a tempered subgroup of GK. This is very useful in certain arguments associated with restriction of scalars. And finally, and this is of course the hardest case, for some lattices in SL2R and SL2C and their low-level congruence subgroups, the Selberg eigenvalue conjecture is known to hold just for, very low-level congruence. In that case, we have a situation where G is tempered in G. This is the hardest case. And then L2 G mod gamma is a tempered representation of G. Namely, it is weakly contained in lambda G. This holds, for example, for SL2Z in SL2R and SL2ZI in SL2C. It's a very special property. And of course, the Selberg conjecture is that you can take congruent subgroups arbitrarily large. But okay, then we're going to have to wait probably for a long time for this to happen. So again, I want to emphasize the point that the last fact is very, very difficult. I mean, okay, for these two lattices, it's not so hard, but extending the congruence is really extremely difficult problem. But the previous ones, they're not so difficult, and they're very robust, and in some sense, they're even generic, as you can see from this example, where every sufficiently high dimension representation actually has to have that property. Okay, and so I'm going to say one last sentence, and then we're going to be done. So I meant this as an introduction to the connection between Diophantine approximation and algebraic groups and unitary representations. And I focused on the exponent of approximation. But actually, in Diophantine approximation, you have much higher goals. For example, already Lang challenged us to prove Hinch's theorem and Schmidt's theorem. And I plan to say a few things about this, but I won't. There is really plenty of work to be done here. We have some recent results on the Schmidt solution counting problem that we were able to establish in some cases. But okay, I guess we're going to talk about this in some other time. So thank you very much for your attention.
Thank you.
And of course, I'll be happy to answer any question.
Yes.
So are there any questions? Then.
Okay, so I would like, as the last speaker, if we keep our traditions, I'd like to take the opportunity to thank the organizers.
Thank you. I mean, we actually appreciated all of you, the 6 speakers. I think you made an enormous effort to convey this on Zoom. I mean, our idea was to cover the subject more broadly than usually. So like Amos' last talk, ergodic theory. So we had automorphic forms, Hecke algebras, p-adic groups. And it was so nice to see, I mean, that each one of you respected, I mean, some sort of maybe, that not everybody understands everything, you know, and is an expert. And I personally found these talks all very excellent and very enjoyable. So thanks to the speakers here, this I wanted to express. Okay, now we come to the fun part. So we have to do our photos. And if you want, this is a carpenter's hat. So I come from a family of carpenters. So if each one of you wants to put on a hat, then we make a group photo, or Job is